All right, good afternoon, everybody. My name's Raphaelle Haywood, and it is my pleasure to introduce Dr. Heather Cegla, who is our colloquium speaker today. Heather is coming all the way from Geneva University in Switzerland as a CHEOPS fellow. The CHEOPS fellowship is an independent fellowship, so she is not a mission scientist for CHEOPS. She does science that goes in line with the objectives of CHEOPS. And so she's been in Geneva for a couple of years. Initially, Heather kicked off her astrophysicist career as an undergrad in Minnesota. So she is originally from the US. And then she moved for her PhD to Queen's University in Belfast in the UK and did her PhD there on magnetohydrodynamics and looking at the impacts of the astrophysical noise sources that come from stars, so from convection, as she's going to be telling us about. Also, she looked at the effect of gravitational redshift coming from the gravitational potential of stars. And then she did a postdoc also in Belfast and then moved to Switzerland in Geneva. And also, Heather is a rugby champion. She played in so your club team actually won the Swiss National Rugby Championship this year.
And we play for CERN, so there's a science connection with the rugby connection too.
Okay, so with that, I'll hand you the floor. Thank you.
Yeah, thank you very much, Raphael. So I'm going to talk to you today about kind of going from two different areas. The first will be a modeling perspective, and then the second will be an empirical perspective. So starting us off, I'm going to talk to you about why we care about the astrophysical phenomena on the surface of stars and what that has to do with exoplanets. Because actually the astrophysical phenomena on the surfaces of stars can prevent our detection of planets, because most of the stuff that we derive about finding planets outside our solar system is based off our knowledge of the host stars themselves. And I'm also going to show you how, in turn, we can use the planets to probe the stellar surfaces. So it's kind of a nice feedback loop of you need to know the planet to know the star, but knowing the planet can help you know the star and vice versa. So starting off, we will go to magnetic activity cycles. So here I'm showing you data from the sun. And so this is over a whole solar cycle, and this is the velocity variation of the sun over that period of time. And you can see that the amplitude from the variations that are happening over a solar cycle are up to about 10 meters per second. And why would we care about that? Well, if you were interested in looking for a true Earth analog, then you want to have a radial velocity precision of 10 centimeters per second. So it's nice to have your transiting things and have a nice Earth-like radii, but if you really want to characterize your planet and know the density and really confirm that you have a planet, it really helps to have the mass. And so that's why most of this talk is going to be focused on radial velocities, because that's a great way of measuring the mass from the Doppler reflex motion induced by the planet. And you can see an Earth analog is up here at 9 centimeters per second. It's really tiny compared to the variations that are happening over a solar cycle. And so we're going to really need to understand the star to be able to pull this out underneath all of that mess. So where does that come from, those variations? Well, one source is from star spots or faculae. So if you have a dark spot, so here is where I'm showing you a solar observation. I believe it's from the Swedish Solar Telescope. And if you have a dark spot rolling into view, and say this is your stellar absorption line that you are using to measure your radial velocities. When the dark spot rolls through, you actually, because you have less light, you get an emission bump in your profile. And that goes around as you rotate there. And of course, you're only going to see that spatially resolved if your star is spinning really fast, but nonetheless, you're changing the center of light of your line profile. You're introducing asymmetries, which then, when you're trying to measure your radial velocity, means you have a sphere's radial velocity. And the same sort of thing happens for faculae or plage, where instead their magnetic fields are not quite as intense as a sunspot. So instead of suppressing all of the convection, they're going and not having any heat flow, so it's being quite dark. For faculae, you are just doing it enough to alter the opacity so that you're seeing deeper into the star, and you can actually see hotter regions of the star. And so you see these bright things here are the faculae or plage. And so then you have the reverse effect. And so these sort of things are going to be tied to the rotational timescale of your star. So for the sun, we have a rotational period of 27 days. And actually, the decay lifetimes are pretty similar to that as well. And so in terms of the velocity shift modulation there, they can be meters per second to several meters per second. There have been times where we have actually confused planetary signals for stellar signals and vice versa. So it's important to be able to understand this to make sure that if we're claiming something is a planet, it's not actually the star. If you want to go to sort of shorter time scales, and then actually at the same time, if you're looking at main sequence things, these are lower in amplitude as well, you also have stellar oscillations. So these are acoustic modes that are being excited in your convective envelope from the convection, which I'll talk about more heavily in a moment. But you have the surface of your star is oscillating, and so you're getting a Doppler shift from the surface of your star moving towards you and away from you. And for the sun, this is several tens of centimeters per second of radial velocity noise, and happening on the time scale of 5 minutes or so. And then the convection or granulation that is causing that, that's also a source of its own type of radial velocity noise. So in this case here, I'm showing you actual solar observations from the Dunn Solar Telescope. And these are from MHD simulations that I'll talk in depth about. And you can see the range of scale here. You're going about almost 30 by 30 megameters on the empirical observations and 12 by 12 in our simulations. And you can see as it moves forward in time, you have these hot bubbles of gas that are rising to the surface, cooling and sinking back down. And as they rise to the surface, they're blue shifted because they're approaching us from our line of sight. And as they cool and sink back down, they're red shifted. And you can see these things are about a megameter in area, and they're brighter. So the combination of covering more surface area and being brighter means that you have a net convective blue shift. The net velocity you measure is blue shifted. And if that was always constant, that would be fine. But it would just be an offset. But if you have a strong region of magnetic field, you inhibit your convective flows, so you actually would get a net redshift there. But even if that's not happening, you still have variability because of the granular evolution. So let's say you take an absorption line profile, cartoon one in here, being the blue one and deeper is coming from your blue shifted upflowing granules. And then you have the red shifted intergranular lane that is darker in these little regions here. And together, if you add those up, you then end up with an asymmetric line profile. So the way that we traditionally look at this is by looking at the bisector of the line profile. And the way you measure a bisector is you take horizontal slices and you grab the midpoints. So if you had a Gaussian, that would just be a straight line. But for the sun, we see this characteristic C shape here because you've got more contribution from the granules, and the intergranular lanes are just kind of depressing this upper redward wing. And so this is moving around on about several tens of centimeters per second. Individual granules can move on kilometers per second velocities, but some of the upflows and downflows naturally will cancel out. But in the end, you end up with several tens of centimeter per second radial velocity noise. So again, if you're looking for a 9 centimeter per second true Earth analog, it's going to be swamped by all of this other astrophysical noise, if you will. And of course, there are a load of different astrophysical phenomena happening on the host star. I've touched in depth only on a few. You also have things like flares and meridional flows. As Raphaelle touched briefly on, you have gravitational redshift. And if the surface of your star changes for a particular reason, then if you're changing the radius of your star, you change your gravitational potential energy. So you get a velocity shift from that. But this is probably a small order effect, less than your 10 centimeters per second, most likely. But nonetheless, once we get better and better instrumental precision, we may need to care about more of these phenomena. Today, I will focus on these two phenomena because that's where most of my work has been centered. Because even if you have the most beautiful, magnetically quiet star, if it's sun-like, you have a convective envelope, you're still going to need to overcome these things. So we have lots of great people, even here at Harvard, working on those big stuff here, throwing GPs at it, and trying to understand the rotationally modulated activity. And so I'm going to talk to you today about convection and oscillations. So we'll start off with the oscillations. So in this example, I'm looking at the sun. And this is the power spectral density versus frequency here. And this is the 5-minute P modes that you may have heard of before. And so those acoustic modes that are being excited by the convection, they're ringing at these 5-minute frequencies. And this is well represented in terms of amplitude by a Gaussian envelope here. And so we're interested in saying, okay, how do we get rid of the oscillations? Can we fine-tune our observational strategy to remove them? Because they cover a narrow range in frequency, so can we filter them out? And so what we do is we look at the Boxcar filter, because a finite exposure time is equal to a Boxcar exposure. And in this particular case, I'm showing you the filter response for 3 different exposure times. And those particular exposure times are related to the stellar parameters of the sun. So that 5.4 minutes, that's where your peak of your P modes are for the sun. And these are related to that. So we just take this plot here of your P mode amplitudes, which is in meters per second, going up to 0.6 there, and we multiply it by our different filter responses, and we see what is left. What's left when we do that? So here I'm showing you the residual amplitude. So this is the radial velocity noise from the stellar oscillations after applying a finite integration or exposure time here. And so this dotted line here is showing you that 5.4 minutes. So let's zoom in on this interesting stuff happening here, because we've got a nice monotonic relationship here. So the empirical observations that have been done so far to try to fine-tune this, that work has just been blindly saying, okay, let's just try 10-minute exposures. Let's just try 15-minute exposures. But this is physically motivated in saying, look, if you do 5.4 minutes for the sun, you are within 1 centimeter per second of that 10 centimeters per second. And if you double your exposure time here, you haven't really gained anything. And even if you quadruple and go all the way out to 20 minutes here, you're only gaining a couple centimeters per second. And the other interesting thing here is because of the way that the filter response is and where these humps are, you can actually do worse when you integrate longer. And so that's interesting, because naively we would think if we just average longer, we're going to beat out more of the noise. But that's not actually always correct. And the reason why this is interesting, this regime, is one, that 10 centimeters per second, that gives you your Earth analog. Also, that's the next generation spectrographs. That's Espresso that is online now. That's Express is hoping to get close to that as well. You know, GCLEF in the future is hoping to get this or beat this. And so it's important. You don't want to be sitting up here at 20, 30 centimeters per second if your instrument can do better. And why waste your time going to 8 minutes if you can do it in 5 minutes? So we can save that precious telescope time and also sample things more finely. So the key here is really that we should be, when we have high instrumental precision, we should be tailoring our strategies based on the underlying physics. And of course, we also looked at how this changes as a function of stellar evolution and different spectral types here. So this is basically an HR diagram that you have with temperature here and your integration time to get to the equivalent amplitude of an Earth mass planet in a sort of habitable zone equivalent quote-unquote area. And then these different tracks are different stellar evolutions. So these are the solar masses there. So you can see for these lower massive stars, you don't actually care about the P mode so much. So they're just too small. You're probably going to need to integrate longer to get your signal to noise than you would to kill your P modes. But this work has been done with Bill Chaplin, and we have a bit of Python code that is publicly available on GitHub. So you can go and put in the stellar parameters, which are your surface gravity, your luminosity, and your effective temperature, and pick your favorite star, and then it will pop for you the exposure time that you should use to kill those P modes to this 10 centimeter or Earth analog regime. And this paper is under review at the moment. We have the referee report. It's a nice one. It's not so bad. We're just doing our best to add some empirical observations to it and some error bars and things like that. And Bill should be resubmitting hopefully within the next week. So soon that will be on archive for you to look at in detail. So switching gears a little bit to granulation. So my argument is that oscillations can be averaged out quite well because they cover a pretty narrow window in frequency space. That is not the case for granulation. So in this case, I'm showing you a few different images of solar granulation. And in this case, you have a G-band single exposure. And then in these other ones here, it's a 1 hour exposure. So we've been together to get 1 hour. And even after trying to average for an entire hour, there's really a lot of structure there. And that's because the granules tend to appear and disappear in the same location. And so the noise is really quite correlated there. And so instead of trying to average them out, we want to disentangle them. And that's where the MHD stuff comes back. So now I'm showing you the same image from before, where we have our 3D-MHD simulations. And they're 12 megameter by 12 megameter, and they're a box. So they're 2 megameters deep. And we run them forward in time, and that gives us the time variability. So we work on about 100 minutes of physical time, which is good because the turnover time scale for an individual granule, the lifetimes are around 5 minutes. So we sample it quite well. And we also want to care about the center to limb implications as well, because we don't just have bird's eye view of the center, we get a disintegrated view. So we need to care about what's happening at the limbs. And so here I'm showing you continuum intensity, and up here you have the line of sight velocity, where blues are blue shifts and reds are red shifts. And you're showing what happens when you go from discenter towards the limb. And as you go towards the limb, you no longer can see to the very bottoms of the valleys, and you can start to begin to see some of the granular walls, and you can no longer see all of the granule tops. And of course, you also have different velocity flow effects, because you don't just have vertical velocities. These vertical velocities come up, and then they go horizontal, and then go back down. And so those horizontal flows at discenter, of course, don't have a line of sight component, but towards the limb, now you get a contribution from those flows, as well as you're still getting some of those vertical flows. And these two things added together then have a net convective blue shift variation over the star. So here I'm showing you center to limb. So this is 80 degrees, so you're not exactly on the limb, but you're pretty close. And then this is velocity in meters per second up to 200 meters per second. And so what I've done there is I've taken a line profile from integrating over this whole area here. I take the line profile that I get from that, and I cross-correlate it with one chosen at discenter. And I average over the time series. So this is really what's the net velocity change relative to discenter. So it's how much that convective blue shift variation changes. So it's not just projected area, because we have those horizontal flows, and we have the fact that granules are blocking other granules, and just the whole corrugated effect there. And of course, we only care about these simulations if they're actually realistic. And so it's important to make sure that we compare empirically to the sun. And so here I'm showing you the particular line that I simulate is the 6302 iron 1 line. And the Lars spectrograph has recently done some really nice high precision measurements of that. And this is, again, that same center to limb versus velocity of the net convective blue shift. And you might look at this and go, yeah, Heather, those two curves are not the same. Maybe you need to go back to the drawing board. But one thing that I've left out is the fact that what we are simulating is not exactly quiet sun. Here we've got quiet sun. In my simulations, I put a magnetic field of on average it's 200 Gauss. In between the individual lanes, it can get much stronger than that. The reason for 200 Gauss is because we really wanted to be able to characterize the magnetic features as well. So we needed a sufficient seed field to be able to do that. But when you have that magnetic field, remember earlier I told you the magnetic field suppressed the convection. And that's what's happening here. You're suppressing those convective velocities. So if we go to a different simulation where we have a net magnetic field of 0 Gauss, you can see we're much more similar to what the sun is doing. We're not going to be exactly the same because we don't have exactly the same magnetic field concentration here. And to kind of back that up a bit further, that what we're seeing is really magnetic field effects. I worked with Steve and Raphaelle and their summer student Michael on this, looking at HMI data. And what they did is they took HMI data, which is a slightly different line. It's a 6173 angstrom line, still an iron 1 line, still deep, shares a lot of the same physical properties. And they look at the HMI data, and they're able to separate based on quiet sun or network, which is a bit more magnetic than the quiet sun, or plage, which is a step even more magnetic. Unfortunately, the satellite has a lot of instrumental systematics. There's this weird 24-hour signal that's in there that they're not quite sure what's going on. So everything is referenced for them to quiet sun at disk center. So these are correct relative to one another, but they're not on an absolute scale, whereas we can be on an absolute scale. The important thing here to look, though, is when they move from quiet to more magnetic, a couple of things happening. One is this turnover here. This turnover, where you're going from more blue shifted to then eventually being red shifted, that happens here more towards the limb as you go more magnetic. And we see the same thing happening here. This turnover happens more towards the limb. And also, they see the same sort of thing happening with inhibiting the convective flows and suppressing those and getting a more red-shifted starting point for their plage, which is what we see here. So the overall behavior is pretty similar. And we also looked at disk-integrated line shapes and bisectors, and those all match well. And if you want to see more, go ahead and check out the paper. But it's incredibly computationally intensive to do all of these things. And if we want to have a sun as a star observation where we've tiled the whole stellar disk with line profiles that are realistic based on the convection properties that we're seeing in the MHD, we don't have the computational facilities at the moment to do this. I mean, we could apply for supercomputer time, but still, I mean, you're talking 20,000 tiles or so if you're looking at this sort of time scale, this sort of size. So what we do instead is we parameterize the signal based off what we know in the MHD simulations. So we separate pixels and therefore the corresponding line profiles based on continuum intensity and magnetic field. And you can see here how I talked to you about that 200 Gauss is average over the whole thing, but in between individual granules, you're up at a couple kilogauss for those magnetic features. And that naturally gives us 4 components. And why did we choose that? It's because we know empirically that the granules are non-magnetic in the bright. And we know that they're the most important component. And so that naturally divided us up based on those constraints. And so for each single pixel in here, we have all 4 Stokes profile, but we're interested in radial velocities. So that's the Stokes I, or your absorption line profile. So that's what we focus on. And so this is the Stokes I profiles for the 6302 iron 1 line based on those 4 different components going from center to limb. And you can see the red and the blue, the funky shape that is going on there, those are magnetic components. So that funky shape is the Zeeman splitting that you're seeing. And the green one that's deep and bright, that's your granule, and then the remaining one there is your non-magnetic intergranular lane. And you might be wondering, why do you have magnetic bright points? And that goes back to the faculae, where you're magnetic enough and you're altering the opacity and you're seeing deeper where it's hotter. So we take these 4 components and we go back to the simulations and we say, okay, from the simulations we have a time series. And that time series means that we can look at the probability distributions of each of these 4 components. And we can use the probability distributions to then build new line profiles that have the same characteristics as the stuff from the 3D-MHD simulation. So that's what we do here, color-coded by the granular filling factor. So the idea is I've generated new line profiles for each individual tile here. The tiles are blown up so that you can see them. And you've got the ones that are inclined. And then the idea is we sum over all of that, and that's our sun as a star. And this is the line profile for each individual observation that's happening here. It may not look like it's moving. This is the bisector. So again, we've taken horizontal slices and grabbed the midpoints. This is amplified by a factor of 30, if I remember correct. And you still don't see it moving. But if you zoom in by like 10,000, then you can see it jumping around here on around the plus and minus 50 centimeters per second, which is cool because that's what I told you we know from the sun. So happy about that. And then the idea is we can look and see how does the convection change the shape of this line, and how do those line shapes impact eventually the radial velocity that we're measuring. And so we can look at a variety of different diagnostics. In this case, I'm showing you a measure for the curvature of that bisector, how much that C shape is, versus the velocity that we measure by doing the cross-correlation function. So in this case, we just picked one observation to be our template, and then we cross-correlated all of our other observations with that one. And you can see there's a very strong correlation between them. And if we just look at this simple linear correlation and subtract that off, we can reduce the root mean square of the radial velocities by about 60%. And so there are loads of different ways of characterizing your line bisectors or your line shapes. So I'll just go over a few of them here. So here again is that C-shaped bisector. And you could measure the asymmetry by saying, let's grab a region on top and average it, and a region on bottom and average it. People call that the bisector inverse slope, the BIS, this one here. Or that curvature, the one I just showed you, that's taking 3 different regions. So it's the same principle, but now you've got another degree of freedom there. And so it's calculated here. You're just looking at differences between those. Or you could say, let's grab our most blue shifted part and compare it to the core, the bisector amplitude. Or you could just measure the line depth. Or you can measure the equivalent width. Or you can measure the full width half max. Another nice one here is bi-Gaussian fitting, where they say, okay, let's have a Gaussian that has an asymmetry parameter, and let's let that asymmetry parameter be different on the blue shifted side versus the red shifted side, and look at what velocity that gives me compared to a standard Gaussian fit of it. Or you can do what is called VASI, and where they measure the slope of the line on the blue shifted side and on the red shifted side and combine it to one weighted average. So there's a lot of different ways that you can probe it. These are just a number of them. And for our particular simulation, these are the results. And so you can see some of them are not so good. These ones are a bit crappy. But a lot of them, you can reduce the noise by about 50%. That means 4 times less observing time is required to get that same level of precision. And so that could be really important when you are trying to characterize a long period planet that is going to take a lot of observations anyways to characterize the orbit. You don't want to have to go even more to be able to nail down the stellar activity. Interesting to note that the normalized line depth doesn't work so well. Why would we normalize it? It's because we're looking at ground-based data. And so to get rid of contamination from the Earth's atmosphere, we have to continuum normalize that. But the equivalent width does quite well, and that's independent of it. So there's a lot of potential here. So our simulations, of course, don't have to be continuum normalized. So we can go a step further and explore and say, what does the integrated area underneath our line profile tell us? Because that's basically a pseudo proxy for the photometry. And so that's what I've done. And here it's just been normalized so that you can see it in parts per million, because that might be a unit of measure you're more familiar with. And you can see what we think as our photometric proxy, it really correlates well. And these are numbers that should be measurable with space-based technology now. A Kepler test, KOPS, they should be able to measure this sort of instrumental precision. And your Espresso or Express or GCLEF should be able to get these sort of radial velocity precisions. So in the future, we should be able to see this, and it shows us that simultaneous photometry could potentially be really an important diagnostic when trying to get rid of the granulation noise. But of course, there are some extra things that matter. I would argue to you that your instrument resolution matters. And that's because what we are using as the diagnostics is the asymmetry. And if you have a lower resolution, you smooth out those asymmetries. So in this case, I'm showing you 3 different resolution modes. They correspond to espresso, because I'm in Geneva, so a little bit of in-house bias there. This is 70,000, the red one, and then you've got 140,000 for blue and 190,000 for the ultra-high. So your standard exoplanet observations are going to be in this blue one here. And you can see that the blue and purple are pretty comparable to each other. You don't really gain too much there. And they get a lot of this curvature shape. But if you go to 70,000 here, it's standing up pretty straight here. So it's going to be more difficult to measure the asymmetries and use those as diagnostics for you. And of course, you should also take into account that real sampling, which is based on your shell grading and the pixels in your CCD. And you can see that medium resolution mode really gets quite wonky there. And so I would argue it's really important to have a high resolution spectrograph if you want to do this work. Also, what matters is the stellar rotation. So we've been focusing on the sun, and a lot of times people want to study the sun and extrapolate to other stars, which of course is a natural thing to do, a natural starting point, because we can spatially resolve it. We have our best data there. But this is just a little bit of a cautionary tale here, because look, this is our line bisector that we have, that nice C shape there. And now I've only doubled the rotation speed. So right now we're at the sun at around 2 kilometers per second. But if we go to 4 kilometers per second, which is still not that fast of a stellar rotation, it's almost straight. You've really lost a lot of your asymmetry for this thing. And then if we go to 6, you've got another shape. It's pretty similar to the 4, but once you go up to 8 kilometers per second, now you're almost doing somewhat reverse. So it's important, one, to make sure that we're fine-tuning our diagnostics, taking into account the stellar rotation, because for a lot of my diagnostics, if I really probe this C bend here, that's the best thing to do. But that C bend isn't here, and it's in a different spot here. So that's important. But also, this really shows us that we really want slow rotating stars if we want to use the asymmetries as diagnostics of what is happening on the stellar surface. Yep.
Can you say a few words about what's happening? What physically is happening when you conduct the rotation?
Yeah, so it's a combination of the line profile shape. So the line profile shape is this sort of C-shaped thing. And then you have an uneven weighting based on the limb darkening. And you have stellar rotation that is symmetric across the axis, like the stellar rotation axis. But then you have radially symmetric center to limb variations of the convective blue shift. So it's a combination of, it's kind of a complicated picture. And once you start spinning up the star, the things on the wings matter more. And so, and you also have center to limb variations in your asymmetries as well. Like if you remember the 4-component plot I showed you as we're going, like your profile is getting a bit shallower and wider as you go towards the limb, because you're starting to get more contribution from those horizontal flows, which are actually faster due to conservation of mass. And so then you get more broadening from those convective flows as well. So it's a combination of a lot of different velocity flows and a lot of different profile shape things. So this will be a different picture too if you're looking at a slightly different line. The iron-1 line is pretty standard for what you're going to have in your typical spectrum, but it's of course important to explore different lines and what shape changes are going to happen. Oh, what have I done here? Yeah. We'll skip that for now. Right, so this is just, before we move on to the next bit of the talk, the more empirical side, this is a summary. So if you've been asleep, this is the time to wake up for the half of the talk. This is your midpoint check-in. So again, for stellar oscillations, I would argue that you can average those out. But if you have high precision instrument, you are going to want to fine-tune that to your stellar parameters. And convection is not so easily binned out. And I would argue for that you want to disentangle. But there's hope for both of these that we should be able to get to that 10 centimeter per second regime. So moving to planets, and how are we going to use those to spatially resolve our stellar spectrum? So similar to what you've got going on here with the moon, now imagine instead of it being the moon, you've got an exoplanet. So your star is rotating, and as you occult some of the blue shifted side that's coming towards you, if you were to look at the disk-integrated velocities, you end up with a net redshift and vice versa. And if you have a different projected trajectory, then you have a different velocity anomaly. If you're only covering a little bit of the blue, you only get a little bit of red. And if you're going over a lot of the red, you get a lot of the blue. So by taking spectra of a planet during transit, this was first detected by Rossiter and McLaughlin for stellar binaries. So, any companion body going across here, you are going to get information about the projected alignment between the orbital plane of the object that you're looking at and the stellar spin axis of what you deem to be your host star. And that's interesting from an exoplanet point of view because it can tell you a bit about the formation, migration, and evolution history. So if you think you had a nice core accretion where you formed in a protoplanetary disk and just chilled out and moved through that accreted stuff, you'd be in a nice aligned orbit. But if you had another companion that swung by and messed you up, you could have some cosine migration and be perturbed that way. Or if you had two jerk planets, you could have planet-planet scattering and kick one out and make one misaligned. So we actually know of quite a lot of misaligned planets. They tend to be around hotter stars, but that's important to help us understand what is happening in these formation, migration, evolution histories. There are a few key assumptions that happen. One is that we assume that those local photospheric line profiles are Gaussian and they're the same Gaussians everywhere. And we assume more or less just solid body rotation. Of course, we know from the sun that the sun differentially rotates, and we know from all that stuff I just told you that the line profiles are not Gaussian. And so these two things have implications. We also know that there's that center to limb variation in the net convective blue shift. That matters. And in particular, if you look at this as a simulation, so imagine you had a pole-on star. You have no rotation that you can see from your line of sight. And you have a 4-day hot Jupiter passing. If you only had stellar rotation contributing to your line of sight, this would be a flat line. But if you have this center to limb variation in the convective blue shift, then this is the velocity anomaly you get. When you cross the bit that is more redshifted, you get the blue shift, and vice versa. And we show in this paper here that if you have moderate rotation, you can actually inject systematic errors in your projected obliquities, which is that spin-orbit misalignment, by around 20 to 30 degrees. And a big contributing factor of this number here is whether or not your local profile is asymmetric. So this includes, like, say you assumed your local profile was Gaussian in your model, but in reality it was asymmetric. Combine that with the convective velocity variations, and you can be systematically off by quite a bit. So that led us to develop a new technique. So for that was two reasons. One, we wanted to really see if we could probe that convective blue shift variation. Of course, we can spatially resolve the sun so we can see it on there, but we want to see what happens for other stars. And that's important for those MHD simulations because we can extrapolate those to K and M dwarfs and F stars. And of course, you find exoplanets around all different types of stars. And so you want to be able to make sure your MHD simulations are not just calibrated against the sun, but other spectral types that you're trying to represent. So for those two reasons, we came up with looking at a new technique. And so what we do is we take the out of transit and minus the in transit. And we look at the starlight behind the planet. And so we're isolating patches of starlight behind the planet along the transit chord. And of course, in order to do that direct subtraction, that's why I've had this light curve bounce down in here. Because we have continuum normalized data, as I told you earlier, to get back on the right scale, we normalize by the light curve. Because when the planet is in, of course, we're blocking out some of the light here. So we need to make sure we're on the correct scale. And this shows you the local CCFs. And by CCF, I mean the cross-correlation function. So you take your spectra and you cross-correlate against a template to get your really nice radial velocities that you measure from your CCFs. These are the local CCFs underneath the planet as you go along the transit. And for this case, I'm showing you here, it's HD 189733. That's a magnetically active K-dwarf. And in exoplanets, we care about it a lot because it's really bright. And that's nice. So that means we can characterize its atmosphere. We can do a lot of things about knowing its mass well. It's these transits for this. There's 4 transits. They've been in loads of papers because they're really high-quality data here. And so you may notice that they're moving a bit from left to right here. And there's also a bit of change here. So part of the change in the continuum intensity is from the limb darkening. And part of it is because if you're on the edge, then the planet is only occulting part of the stellar disk, so you just have less light. And if you like Doppler tomography, you may like the bottom plot here, but it's not important. If you don't, if you hate it, this is showing you velocity versus phase, color-coded by the flux. So this is the planet that you see moving through here. So we look at these local CCFs where we don't have to assume anything about the local profile. And of course, that's why the Rosetta-McLaughlin comes back in, is because these things are rotating. That's why we see these velocity shifts going on here. And here I'm showing you those velocity shifts as a function of phase, or if you prefer, if you're a stellar kind of person, you can look at stellar radius there. And this is your local RV here. And then if you're another stellar kind of person, you got your mu, which is your center to limb angle. That's your color. The color of your error bars tells you the transit. Those are different transits. And you see that the velocities change from about -3 to +3 kilometers per second. And that's because the V sin I of the star is around 3 kilometers per second. And you may also notice this inset here where I'm showing you latitude versus phase. And the way that we can pull out the stellar latitude underneath the planet is because we allow for differential rotation. And the reason we are really motivated to allow for differential rotation is because we wanted to try and isolate the convective blue shift variation, which is on the same order of magnitude as a differential rotation. So if we assumed solid body rotation, we would get it wrong. And for this system, we can only put loose constraints on alpha. Alpha is how much differential rotation you have. For the sun, the alpha is 0.2. And we can say with 99% confidence that alpha is greater than 0.1. So we know that there's differential rotation. But because we have a low projected obliquity and only a little bit of stellar inclination, our 3D obliquity is only 7 degrees. And so we only cover a few degrees in latitude here. So it's really only at the limbs that we're probing different stellar latitudes. But of course, if you had a system that probed more stellar latitudes, you should be able to constrain this more. And I have upcoming time on Espresso that I was awarded through the open time call, where we're going to try and do this with Espresso and more finely tune this. We've also applied this to a G dwarf. So HD 189733 is a K dwarf. We looked at an M dwarf, WASP-8. We actually found that there was a local variation in those cross-correlation functions in the contrast, or the depth of those. And if you had the classical method and assumed it was constant everywhere, you're 20 degrees different than what we get. Originally, we thought this might be astrophysical. Now we have reason to believe it's instrumental. Nonetheless, it's in the same data set that the original authors used, and it biased their results because they didn't take it into account, which fortunately is a strength of ours. And we've also detected the first spin orbit alignment angle for an M dwarf. So we've shown that we can really go cool with this technique. So that's really important if you want to characterize your M dwarfs. So I encourage you to go and check those out. Of course, I'm a stellar kind of person, so I'm interested in that convective blue shift, remember? So we took our model for what we believe to be the velocities from our best fit, and we subtracted those off. And that's what is left here. So if we remove the stellar rotation, what we should be left with is the convective blue shift variation. And these are simulations from 3D-MHD simulations of a K-dwarf. We're back to H2189 because it is the brightest target that we have, our best signal to noise. And you can see we've done 3 different iron lines. The pink one is the deepest, and then the brown one is shallower, and the gray one is the shallowest. And we did 3 different magnetic fields. And you can see there are trends in both magnetic field and line depth. but unfortunately, we can't really say that a cross-correlation function behaves more like an individual one than the other, but we lie smack on top. So this still provides observational evidence that we are in agreement with the MHD simulations. And so this is the first stuff that was done for this kind of validity check on a K-dwarf that's main sequence. So anything other than the sun that's main sequence. So that's pretty important there. So the takeaways for this half is that traditional RM measurements, Rossiter-McLaughlin, those in-transit spectroscopy, they often assume solid body rotation in a constant Gaussians. We don't want to do that. That can introduce systematic errors. With the reloaded RM technique, we don't have to assume shapes on the profile, anything about the profile shape. We can allow convective blue shift to contribute, which could be important for things like F stars, your hotter stars, where it's going to be a bigger issue. And we can lift the degeneracy on the V sin I if we have differential rotation. And that means we can get the 3D obliquity. And to date, there's only like 15 3D obliquity measurements. And this is the first self-consistent technique to do that, because most of the time, radial velocities would have to go to photometry or some other type of technique to be able to do this. And we can go all the way down to really cool systems. So to summarize, stellar activity is an issue. The astrophysical phenomena on the surface of your star is not homogeneous, and it is not static. So it impacts our radial velocities, which means it impacts our measurements of planets when we're trying to measure the Doppler reflex motion of a planet. And even if you have magnetically quiet stuff, you're still going to have a problem if you have a convective envelope. But you should be able to average out your P modes or your stellar oscillations, and there is good hope for disentangling the convection. And of course, this really means we need to know the star to know the planet, and vice versa. The exoplanets can feed the other way. So we can really use planets as probes of stellar astrophysics as well, and gain more knowledge about the star that will feed back into our characterization of the planet, at the same time learning about the evolutionary history of our planets. So I'll take any questions now, if you have them.
Of course, for any normal astrophysicist, this is completely terrifying. But there's another way of measuring masses when things are fortunate is transit timing variations. Is there an example where, for one system, you or somebody else has gone through all of this and got an RV mass, and then also had a TTV to check against it, and did it line up?
Yeah, so there are cases where we have measurements of both, and there are some discrepancies, if I remember correctly. I mean, Raphaelle would probably, she's the one who measures masses on a regular basis. I don't know if you know. I know that there are sometimes differences, but I think also you can get more precise masses with your radial velocities as well.
Yeah. So Nuka and Malavat recently published at least one paper on, there was chapter 9, right? Where there were initially in previous studies, so they had TTV masses and radial velocities, and they didn't agree, but then they redid it and found agreement.
You just keep working till you get agreement?
and this does have implications for TTVs though as well, because you have a finite number of granules. And so when your planet is crossing them, you're going to have variations because you're covering different amounts of granules and stuff. So it's possible that once you reach a certain level of trying to get high precision on your TTV masses, you could end up needing to care about the granulation again from that point of view.
I'll go off on more of a detailed observational question. So with HD 189733, I was sort of fascinated that it looked like you were covering different latitudes as the planet went across, but in general, it's going straight across. So is this a projection effect?
Yeah, it's because your star is, the stellar inclination is not exactly 90 degrees. So your lines of equal latitude are curved relative to a 2D projection.
Right, so it's still orbiting in the it's still a planar orbit, but because of the inclination, so that sort of feeds the next question of, so you have the possibility here, and of course we've seen a lot of this with Kepler, of sampling different active latitudes. Are we getting to the point where we're going to have to know statistically how active any given star is before we can then feed back into how accurate an RV model we're going to be able to obtain for that particular star? Because any given transit is going to have different noise qualities to the next transit after it. So is that difference going to matter, or can you simply be so self-consistent in a single observation that you solve it and you don't never have to look back?
Yeah, it depends what kind of measurement you're interested in. Like if you're interested in using your transit, your spectroscopic transit, either for transmission spectroscopy or for getting your 3D obliquity, yeah, you're going to need to find some way to figure out if you're occulting active regions or if there are active regions that are not occulted. There's a lot of stuff in the literature that shows that even if you have an unocculted spot, you're going to bias your planet radius measurement, which biases your atmosphere interpretation, so it's important for that. In terms of my stuff, one thing that really helps us is to have a simultaneous light curve. Because in the light curve, it's easier to see the spots. It's quite obvious if your planet occults a spot. And so the other thing I'm doing with my espresso observations is we're looking at an active star. So one that in the past has occulted spots several times. And we have NGTS and OILCAM, the Swiss telescope. We have two different telescopes giving us simultaneous photometry to go with our espresso RVs. And we're trying to see if we can isolate the starlight from an active region as the planet goes across it. So those, I'm basically waiting for Christoph Lobis to run them through the pipeline. He's got a lot of stuff on his plate with the espresso pipeline. And once we have the data reduced, that's something we'll be looking into. And then that can help us characterize the models as well and help us figure out better ways to reduce the activity effects.
So to follow up, then with something like GCLEF, it would be beneficial to have simultaneous multi-wavelength photometry to disentangle this.
Yes, it would definitely. I am also working on a chromatic reloaded RF. And part of that is because the stellar rotation should be achromatic, but the planetary radius, or that light curve that you would use to normalize it, is chromatic. And so the idea is if I have one reference band and I know my velocities for that one reference band, then I can use that to back out what's happening at different wavelengths. So that's a work in progress at the moment to see if we can do that. Otherwise, the alternative is to have simultaneous photometry.
In a similar vein, have you tried out looking at, for either of these two halves of the talk, looking at different mass cross-correlation masks?
Yes, yeah. For HD 189, we did try to do different masks. So I tried a few different templates. I said, like, okay, let's take all the shallow lines and all the deep lines, all the lines with low Landau factor and high Landau factor for different magnetic sensitivities and high excitation and low excitation, and look to see if I could see differences, but I just didn't have the signal to noise to do it. And so I think it's something I'll revisit with espresso data when I can get my hands on it. Perhaps if the GTO people play nice with me, maybe I can get some of the bright stuff for looking at something like this. And also have talked with Xavier Demusk about his sort of line-by-line analysis and trying to target. He's looking at and saying, okay, these are the active lines based on his analysis, and these are the inactive lines, and that could be our next step of trying a template on that as well.
Am I right in kind of imagining that, another parameter, irrespective of sampling resolution, you can add more lines to your mask, which increases your information content perhaps for the RVs,
exactly.
That might wash out any bisector variations.
Yeah.
Is that a potential problem?
Yes, it is. So there's one of the reasons why we couldn't see a difference when we went to those different templates is, like you said, we just had less lines, so we had less signal to noise. But you're absolutely right. Once you start mixing all these different lines, then you have competing effects. And actually, the way that the cross-correlation functions are done now, they're weighted by line depth, so we don't actually preserve the bisector shape in the same way. So we're still trying to characterize the CCF asymmetries, but they're not necessarily representative of just having a weighted line profile. And so it's important to try and in the future figure out a way to try to preserve that. That's something that's been on the back burner that Xavier and I had talked about before, and Christoph and I, and hopefully in the future we might be able to revisit it.
So just to clarify, the plots that you showed with the different correlations, they were for they weren't actually for CCFs.
For this stuff here?
You derived those from the true line profiles. Is that?
It depends which part of the talk you're talking about. If you're talking about the convective simulations, that's one line profile.
Okay.
And so there's no, like, yes, we have a CCF, but the CCF in that case does preserve the bisector, because the CCF is just, we've taken one line profile and cross-correlated with all the other line profiles.
Okay.
So we don't have like a template mask of delta functions that are weighted and done like that. So in this case, when we just take one line profile and cross-correlate with the others, we're preserving all of the information from the line shapes.
So that's what we need to do for with our regular RV observations, basically.
Yeah, possibly. I mean, maybe you gain, but I know that if you weight by line depth, you can gain in RV precision. So
yeah, that's the thing.
You have to decide what is more important to you. Maybe there's a way to do it without having to lose one. I'm not sure. Or maybe you do one way to characterize what the line shapes are doing, and you do another way to get your RVs. and that kind of folds back into our convection stuff. So yes, so often a criticism that I get is that we've simulated one line profile, and people are like, whoop-de-doo, you have thousands of line profiles in your Spectra. But if we pick strategically line profiles that have given characteristics, then they can be representative of lots of lines. And it's possible that maybe we only need to look at like a handful of lines to get an idea of what is happening on the spectrum as a whole.
James?
You presented the case of WASP 8b, where assuming solid body rotation, you underestimated the obliquity of the planet. I was just wondering, the relationship between the host star temperature and the obliquity of the planet, could it be that cooler stars have their obliquity, the planet obliquities underestimated because of using solid body rotation? And could that relation be removed by revisiting it with differential rotation?
Yeah, there is an element of that. So when we did HD 189 and we put the constraint on the differential rotation, we did see that we have a systematic difference based on what you would measure if you assumed solid body, or if you just did your other ways of measuring it. And so I think that there is a systematic offset that you are skewed if you ignore the differential rotation and it's dominant there. I don't think that is going to bring you from a line to misalign. I would be surprised if you could go from 100 degrees obliquity to down to 10. But I don't know, it's something that maybe for a fast rotating star where the differential rotation maybe could be a big issue or something. But for WASP 8 in particular, it was not the differential rotation that skewed things. It was the fact that the local profile is changing. And so in the case of WASP 8, we didn't actually have the instrumental precision to justify the extra free parameter that would be differential rotation. And so our best fit model, when you're penalizing for free parameters, was solid body rotation. But because the local profile itself, the contrast of the local profile was changing, that was what contributed to the difference with the value in the literature at the moment.
Okay, so we have 1 minute left for a very quick question. Joey?
So you mentioned that there's only about a dozen systems where you've had this
the 3D obliquity.
3D obliquity.
Yeah.
And so I'm just curious, what is the distribution of the stellar types for that population? Is it all massive, rapidly rotating stars, or is it kind of across the board? Outside of what was here.
Yeah, I don't remember off the top of my head. So I know that sometimes they have the 3D obliquity because of the photometry. And so the photometry can give you the rotation period, and if you have the V sin I from the spectroscopy, you can break it that way. And sometimes they get it from astroseismology. You can get the stellar inclination that way. And if you get your stellar inclination from the astroseismology, those ones are going to be more evolved on average, because that's where the precision is for those measurements. But for the ones where you're getting it from the photometry, you could come from a different range. But of course, your photometry can have degeneracies as well, and there's a whole lot of potential problems of, like, are you measuring the real rotation period? Are you measuring a harmonic of it? Are you getting the active regions decaying? And are you measuring differential rotation from when you're looking at your active regions and your period changing, or you just, there's photometry has a whole host of degeneracies that we can avoid if you go to the velocities.
Actually, Shani Nava, a grad student here, is working at the moment on an analysis that shows just how difficult it is to actually measure rotation periods with any sort of precision and accuracy. So definitely a good idea to get around that altogether.
Yeah, and then the other nice thing is we're self-consistent, so we don't have to go to another technique. So anytime you're going to another technique or another instrument, you've got different systematics and different things, different biases from those that you should be taking into account. So it's nice if you can have a self-consistent one, and it kind of comes for free,
Okay, so Heather has a couple of slots left in her schedule tomorrow morning. I think it's 9 a.m. But if you want to keep with her, sign up quickly, and let's thank Heather again.
Yeah.